So hi, once again, I'm Zach Ulibarri, and I'm a grad student at the University of Colorado, where I work at the Impact Dust Accelerator. And today I'm going to be talking about a couple different experiments we have there where we're looking at the interaction between dust and ice, and again, about how this can create or change organic chemistry on the surface of Europa, and also for the survivability and detectability of organic chemistry for SUDA, the surface dust analyzer, which will be on the Europa Clipper. So I'm just going to kind of fly through my introductory slides, just to briefly remind you of stuff you all know. We saw this cartoon yesterday along with a couple other potential ones. Again, we have reason to believe that there's a subsurface ice ocean, or excuse me, a liquid water ocean. And of course, we know that there are these plumes on Enceladus, which is a similar icy ocean world. And there have been various papers that convince us that these plumes are probably coming from the subsurface ocean. And for the case of Europa, there have been some hints from the Hubble Space Telescope, which would suggest that there are similar plumes at work on Europa. And more recently, for looking at old Galileo magnetometer data, there seems to be corroborating evidence coming from that's completely independent. And so all this is to say is that perhaps this cartoon is actually pretty accurate. Perhaps there are these plumes that are ejecting material from the subsurface into the local environment surrounding Europa. And so whether they're coming directly from the subsurface ocean or other subterranean features. And so what that's saying is that the local volume immediately surrounding Europa is potentially rich with these icy dust grains coming from the subsurface. But even in the absence of these plumes, there are other processes that lift off dust from the surface itself. So for example, there are cosmic or interplanetary dust particles, and when they strike the surface, they kick up a great deal of ejecta. And in fact, in the case of ice, if you have a particle of mass m that strikes the surface, you can generate several thousand m worth of ejecta. And so even in the absence of these plumes, there are these interplanetary dust particles that are constantly kicking up yet more dust. And so, in other words, when you look at Europa, this is not the complete picture. The complete picture is something like this. You have all these different icy dust grains on these ballistic trajectories, whether they're coming from coming from plumes, coming from the subsurface, or from interplanetary dust particles coming in, hitting the surface, and kicking out other ejecta. And this, of course, gives us a tremendous opportunity to study the composition of the moon without actually landing. And that's one of the many goals of the Europa Clipper. So for example, there's the SUDA instrument, the Surface Dust Analyzer, which is an impact ionization time-of-flight mass spectrometer. And the objective of it is to fly around and scoop up these dust particles and study their chemistry. But of course, like any type of spacecraft instrument, we need to have laboratory support to understand how it works, to understand the physics behind it, and learn what types of chemistry it can or cannot detect. And that's the first part of my research that I'm going to be talking about. And so once again, I work at the University of Colorado Dust Accelerator. Here's a picture of our system. Here's our high voltage Pelletron, which is kind of like a Van de Graaff generator, but it uses a chain instead of a belt. But so this gives us a high potential, and we kick particles down our tube here, and then they reach our target chambers at the end. Now the accelerator is capable of giving us particles of up to a micron in size at velocities of up to 100 kilometers a second, although typically we shoot between 3 and 30. Iron dust is our workhorse. But really, we can shoot most things that are conductive, and if it's not conductive, we might be able to wrap it in something conductive and shoot it anyways. So here's a system diagram. Again, here's our Pelletron, which is our high voltage source. And so we put our dust source in there, and the Pelletron is capable of giving us up to 3 megavolts of potential. And so the dust particles get kicked around, and then some of them go through that 3 megavolts of potential, which kicks them down our flight tube down to our target chamber. And again, we can accelerate them up to 100 kilometers a second. Now we have various detectors in our system. So for example, we have our DCS system, which is our dust coordinate sensor. And this allows us to actually get the full 3D flight trajectory of at least some of the particles, typically the high charge ones, which tend to be a lot bigger. So we can see where the particles are in our system. We also have various detectors that give us some more basic information about the dust. So for example, its charge, its mass, its velocity. And from this, you can actually work out an estimated effective radius. And so this is important because we can't actually control what the dust source is doing. The source spits out dust at a wide variety of masses, velocities, and charges, or anything like that. But what we can do is we can measure those particles non-destructively in flight, and then feed that information into our PSU, or particle selection unit. And then that system in turn controls an electronic gate, which actively kicks out any of the particles that don't match our criteria. And so while we can't control what the dust source is doing, we can say, okay, I only want to look at, say, particles between 5 and 10 kilometers a second. And so the PSU then sends a timed pulse that opens the gate just in time for the particle to go through, and then the gate closes right behind it. And so the particles then that meet our selection criteria will go into our target chamber, And we have a number of different targets, but for the purposes of studying the composition of Europa, I'm going to be talking about the cryogenic ice target that we have. Now, there's a couple different ways we make ice. The first of which is vapor deposition, which is our simplest and, our simplest method. So we have our copper block here that is actively cooled by flowing liquid nitrogen coming in these tubes at the bottom. And then on the surface of that copper, we put a sapphire that's coated in gold. And so we then allow a very small amount of water vapor into the system, and the water moves around, and because the surface is cold, any water particles that touch the surface freeze instantly, and so over time you grow a surface of ice. Now, because the surface of the sapphire is coated in gold, you can actually bounce a laser light off of it and do interferometry to measure the thickness. We can also control the temperature at which the ice is grown, so we can form different crystal structures. And so this is a very controlled way to grow ice, controlled way to grow ice. And it's especially useful for simple mixtures such as water or methanol, things that evaporate very easily. However, not everything evaporates very easily. So let's say if you wanted to make salt water, for example. If you have a glass of salt water and you let it evaporate, the water evaporates, but the salt sticks behind. And so it's not as easy to vapor deposit using that. Similarly, if you froze that glass of salt water slowly, you'd find that you get chunks of pure salt surrounded by chunks of pure water. So you don't have an even distribution throughout the ice. So to get around this, we have our flash freezing system. So here you have this upper L-shaped assembly here, which is removable from the rest of the copper block. And we put a couple drops of whatever solution we're interested in studying into our target plate, slide this Vespel cover into place, and then throw the whole thing into liquid nitrogen, so it freezes very, very quickly. And the idea then is that the the salt particles, say, won't have time to move around, but they instead freeze in place. And so you have a more or less homogeneous distribution throughout the ice. Now, we can do all kinds of stuff with this. Like I said, we can do salt water or salt ice, but we can also dope amino acids and other types of complex organic chemistry that we might be interested in studying with Suda. So here's a system diagram. So here's our target in the center, which again, we can either grow through vapor deposition ice onto it, or we can install flash frozen targets. And we expose the ices on that target to particles coming from our dust accelerator. Now, because these particles are traveling at several kilometers a second, when they hit the surface, they explode and create a plume of ejecta. And there's so much energy released that you also ionize many of the particles within that ejecta plume. And so here I have my little cartoon. So I'm going to say that these blue particles are lightweight and the red ones are a lot heavier. So because they're ionized, we apply electric field, and that shoots them down our time of flight tube towards a detector here. And of course, we give everything the same kick, which means that the lightweight particles move down the tube faster than the heavy ones, right? You kick a tennis ball, it goes fast, a bowling ball, it goes slow. And so if we look at the signal that our detector sees here, we have just a bunch of noise because nothing's really happened yet. And then sometime later, you see a spike associated with the lightweight blue particles showing up at our detector. And then sometime later, you see another spike coming from our heavy detectors reaching it. And so what that's saying is that each of these spikes is associated with a different population of ions at a different mass because they spread out in time according to their mass. So this is an example spectrum looking just at pure water. Again, we have time here on the x-axis, and all these different spikes correspond to different populations of ions. But because they spread out in time according to the mass, we can convert that time axis into a mass axis. And then from that, we can figure out what the chemistry of these independent spikes are, because if you know something about the mass, you know something about the chemistry. And so that's what we're doing. We're studying the chemistry that is produced in this impact plume. So again, this is pure water. So this is actually a characteristic water cluster sequence. You see water 1, water 2, and water 3. That's 1, 2, and 3 water molecules all grabbing together. But you see that the dominant cluster sequence is actually this W1H, W2H, and so on. So that's protonated water, water plus a single hydrogen atom. And that's how it tends to ionize in these impact events. Now, this is a simple water spectra with just water by itself. But like I said, we can do all kinds of stuff with this. We can add complex organics and a whole bunch of other stuff. And so now that comes into like more of the scientific motivation, especially as related to Suda. So we know that time of flight instruments on flyby spacecraft seek to measure organic chemistry in icy dust grains. However, there have been experiments in which single amino acid molecules have been shot at solid targets and they're shown to fragment at typical flyby velocities. However, it's also true that organic chemistry in ice may be shielded from impact stress by the ice matrix itself. And so then the million-dollar question is, of course, does complex organic chemistry in ice survive impact at typical flyby instrument velocities? I'll give you a hint, the answer is yes. What we did is we used our flash freezing system to dope water or ice with lysine, a simple amino acid. Then we shot it with dust at impactor velocities that are relevant to the flyby speed of the spacecraft. We see here's our water cluster sequence, and we also see here's our lysine. In fact, we see lysine and lysine 2. So that's 2 lysine molecules gripping a single hydrogen atom. Now this is an impactor traveling at 6.7 kilometers a second, which is significantly faster than the typical flyby velocity of the Clipper, which is something like 4 kilometers a second. And so what that's saying is that this chemistry survives the impact process. It doesn't fragment, and you can measure it directly. Now we can do this with a number of other things. And so, for example, we have here lysine-glycine, which is a dipeptide, like dual amino acid chain. So 2 amino acids grabbing the same thing. And so there's our lysine-glycine line. And again, this is an impactor traveling at 4.8 kilometers a second. So again, what this is saying is that this complex chemistry, even this lysine-glycine, which is more fragile than the single amino acid by itself, survives the impact process and can be measured. But we can there's also some other interesting stuff. So this is a spectrum with histidine. Of course, there we see our histidine line. This is an impactor traveling at 3.2 kilometers a second. But there's some other interesting stuff here, namely these sets of lines right here. So I have 83 highlighted, but there's actually 81, 82, and 83, along with 110. Now, for various reasons that I don't really have time to get into, that 81 line I don't actually think is something relevant to that. I think that's more related to something like a contaminant in our system, perhaps related just to the copper. But the 82 and 83 and 110 lines are all important because if you go to the NIST website and look at the electron ionization mass spectrum where they intentionally shatter histidine and other amino acids, this is what you find. You see lines at 81, 82, and 83, and 110. Now, of course, the ratios here are very different. We have very different line strengths compared to these. But the point is that I'm starting to see these in a lot of different spectra. And so what this is looking like is that this is a repeatable fragmentation pattern for histidine. And so what that's saying is that even if the histidine breaks up, you can still detect it by using these fragmentation patterns. And so what I'm saying is that perhaps fragmentation can even be turned into our friend, and we can actually use it as another way to identify the amino acids. And so now I'm going to change gears completely. So let's just forget about the spacecraft for a second, and let's just talk just about Europa and the fact that there are these interplanetary dust particles coming in. And so now I want to talk about what happens when you go to a much higher velocity. So again, I have this cartoon where this red impactor is coming in and it's kicking up a whole bunch of ejecta here. What if we go to much higher velocity? Well, you're adding a lot more energy to the system, and then you can start changing the chemistry. So with pseudo, we wanted to avoid changing the chemistry. We don't want the particles to shatter and form new molecules. But if you have a high enough energy impactor, you can do that, and you can change the chemistry. So in other words, this could be a mechanism for changing the composition of the surface of Europa. So what we did here is we bubbled gaseous CO2 through water and then froze it using our flash freezing system. And we actually did this just to see if we could even detect the CO2 at all. And we see it right there. There's our CO2 line, and again, it's protonated. This is an impactor traveling at 17 kilometers a second, so over 4 times as fast as the Clipper flyby speed. But we see CO2 at a wide variety of velocities, all the way down to 3.5, all the way up to 20. We see it all over the place. But at these higher velocities, you see some other stuff. For example, you see CO. And so what we're doing here is we're changing the chemistry. This is an incredibly small baby step, but it's an important one to be sure. CO is a volatile. So that means that this is a mechanism to replace some of the volatiles on the surface. Now, the other thing that's interesting about this one is that there's this line here at 32. Now, we're liberating hydrogen, we're liberating carbon, and we're liberating oxygen just because we're coming in at so much energy, we're shattering everything. 32 could very well be O2, because O is, of course, at 16. But O2 likes to charge negative most of the time, and this is a positive ion spectrum. So it's a little bit weird. It could also be something else. Again, we're liberating H, we're liberating C, we're liberating O. This could be HC3OH. This could be methanol. We're not really sure yet. And so the way we're going to figure this out is we're going to do the same experiment again, except this time we're not going to use normal CO2. We're going to use CO2 that uses carbon-13. And so if this is in fact methanol, then this line will shift over and it won't be at 32 anymore, it'll be at 33. And then we'll know that we're actually creating slightly more complicated organic chemistry through this impact process. So with that in mind, the upcoming experiments that we have, specifically with regard to the generation of organic chemistry, is exactly that. We want to use our carbon-13 CO2 to see if we're generating methanol. We also want to see if we can even just generate CO2 and CO through dust impact. Say, what if we shoot a carbonaceous dust impactor into water ice? Can you create CO2 and CO? We also want to then step up the complexity, and the sky's the limit at that point. I mean, perhaps we might even be able to generate amino acids someday. We'll see. Then with regards to our detection of organic chemistry, we have a number of different experiments. So one of the things we're doing right now is we're looking at known linear combinations of amino acids. So let's say I make a 50-50 mix of histidine and lysine. Can I use that? Can I look at the relative line strengths to tell me something about the relative concentration of those amino acids? Because the relative concentration is what's important for a lot of the biosignature detection using amino acids. So we're looking to see if that's something we can use. We're also going to continue looking at fragmentation to see if we can, again, use it as a fingerprint to further identify these amino acids. And we also want to add some salt compounds to see if and how that changes our detectability. And so with that, thanks a lot. I'm happy to answer any questions.
Questions?
Hi. All right. So yeah, it's a good work, and I hope that you can detect amino acids too, because that's what I'm interested in. The question here is, I would not be very surprised that you could still see some fragment amino acids, because in your experiment, the concentration is pretty much high. That is, it's very ideal. It's like 1 molar or 0.1 molar. The question is how much percent that you could retaining after your fragment. And the other question maybe is what would be the temperature increase after the the dust particle after the impact, because the temperature increase decide how much percent of amino acids will survive. Yeah, and it's I believe that even with a very high flyby speed, 7 kilometer per second, but if the I don't know, I haven't done any calculation for that, but if the particle size is very small, even with a very high flyby speed, we relatively doesn't have a lot of kinetic energy, so we can still retain substantial fraction of amino acids.
Sure. So with regards to the temperature, so when the particles hit, we've done the calculations. The amount of energy we're adding to the system is very small compared to the cooling power that we have, and so the temperature of the ice surface itself doesn't really change. If that's what you're getting at. Within the plume itself, I have no idea. All I can say is that we see the amino acids. And so yeah, and then with regards to concentration, yes, we are using very high concentrations, and that's kind of because we're getting this experiment off the ground and we're going after the ideal case. And one of the things we absolutely want to do is look at the minimum concentration to determine what that limit is. And so yeah, that's one of the things we're working on.
Sorry, quick follow-up on that. So you're saying the temperature of the ice doesn't change on impact?
No.
So there should be no meteoritic crystallization, induced crystallization on all the solar system bodies out there in the...
Wait, I'm sorry, say again?
So if the temperature doesn't rise around the impact site.
Mm-hmm. Oh, so what I'm saying is that, so around the impact site and in the plume, I do not know. All I'm saying is that over long periods of time, repeated dust impacts are not going to significantly change the surface of the ice itself in a large area.
Have you looked at the impact sites with some kind of spectroscopy at all?
I have not.
Yeah, nice talk. Very nice results on the fragmentation and on the chemistry that occur in the plumes. I have a question about the results where things did not fragment. Were the experiments using high-energy iron particles into a mixture of lysine and water, and then seeing that the lysine did not fragment upon ejection? Mm-hmm. Well, that to me is different than actually detecting lysine in the spacecraft, where the spacecraft is going 4 kilometers per second, and the lysine hits the spacecraft.
Sure.
Because you could have the lysine ejected through spallation, which is low energy, and therefore not fragmented. So have you thought about to extent more fragmentation could occur in the spacecraft sampling, where it's not really, there's 2 steps occurring in your experiment, whereas in the spacecraft you're directly hitting the lysine at 4 kilometers a second. Mm-hmm. There's a difference.
Sure. So so I mean, what we effectively have here is like the reciprocal of the real life system, right? So we have an ice surface that is impacted by a metal dust particle, whereas the spacecraft will have a metal surface impacted by the icy dust grain. And so, I mean, The answer is that we're still looking at the chemistry of the plume, and that's why we think that it's still relevant. But we are also working on an icy dust grain accelerator, and then we could shoot icy dust grains directly into SUDA, but that will take some time.
Other questions?
I have a really basic question. Is that on?
I think so.
Is the predicted flux for high velocity particles, interplanetary particles coming in at rates high enough to cause a change in chemistry? Is it predicted to be significant enough to cause a change in the detection of surface chemistry?
The answer is I'm not sure. I haven't. The numbers that I've looked at were really only relevant in, like, say, the SUDA proposal, where they're talking about these particles coming in and kicking up more ejecta. In terms of the, we're not even at the point where we can quantify the level of change that these particles have, like how much changes, and so I'm not I can't answer that question right now.
Yeah, two things. We mentioned this also for the energetic sulfur ions and things. And the first thing is that should be worse in terms of local heating of the ice, but when the ejecta comes out, it sort of self-cools, and so the ejecta can stay intact somewhat, which is interesting. But when you said that you produce CO, that's CO plus, or CO hydrated, is that right?
We actually see a couple different lines. So we see CO and what we think is COH, and so the answer is
These are ions, so.
yes, ions, yes, positive ions. Yes.
So, do you have any idea what your neutral ejecta is like at all? No.
No.
Okay. Because the chemistry, these would be swept away or something. Okay. Okay. Thanks a lot. Oh, one more thing. Yeah, I want to ask. People have a good idea of what the dust environment is. Let's forget the plumes. Without plumes, they have a good idea that there was a dust measurement. Early, it was far, not so close. Have you measured the probability of counting and the population in the ionosphere?
So that's something like it's again. They did a lot of estimates for this in like the SUDA proposal. The number that's coming into my head was that like at the closest flyby we'll get like 5,000 particles. Do you know? Thousands. Yeah. Thousands. So thousands of particle per flyby.
It's about 40 particles per, I think, a second or something like that. Yeah, at 25 kilometers. That was the estimate. So I think following Bob's actually comment, though there will be at hypervelocity impacts, regions that experience extremely high temperatures, transient temperatures.
Yes.
The ejecta actually may not be heated so high to actually, do the chemistry at, let's say, at 6 or 5 or 8 kilometers. But as you go to 17 and 20 kilometers, even then, you may still retain some, material without doing chemistry. There are experiments and theoretical work of, I think, I forgot his name, where they shock the ice to that particular velocities, almost like a comet impact on Earth, and show that you can actually synthesize amino acids in that.
Right. So like light gas guns.
Exactly.
Right. They produced, I think, lysine.
Yeah. This is Nir Goldman. Exactly. Nir Goldman. Yeah. So. You not only do chemistry to destroy, but also you can make it.
Exactly, and that's exactly what we're trying to look at here. Yeah.
Just a quick question. I see an iron peak there, and I saw sodium in some of them. Is that the impactor, or is that something?
Yes, probably. So let's see. That's probably not the best one. There we go. So you see some potassium and some sodium here. Those are contaminants, probably on the iron dust that's coming in. And the iron itself is also, it's just coming from the dust itself.